Yeah, thank you, everyone. So we're going to start the talk. I just want to start by thanking my co-workers. This is joint work with Alex Bradbury and Andy Wingo. I'd like to thank the Google WASM Tools team for suggestions and discussions the last couple of years about this, and Bloomberg, who have been sponsoring this work. So let's start. WebAssembly. The WebAssembly is a virtual machine, so it's a language that runs on a virtual machine. And it has a specification, an open specification, it's online. And one of the things that I would like to clarify at this point is that I'm going to talk a little bit about, sometimes referred to the host system. The host system is the system that basically implements the WebAssembly virtual machine. And for the purposes of this talk, because I'm interested in how WebAssembly interacts with the web, it's the host system is JavaScript. So WebAssembly is a Harvard architecture. We have basically well-typed functions arranged in modules. There are some interesting peculiarities where some things you cannot get access to the address of, like model level globals and function level locals. You cannot access it. It's also a stack machine, but the stack is implicit, so you cannot actually access the stack. And then in the beginning, it was a very simple machine, right? It had only 4 numeric types. So those were the only types available in WebAssembly. And those are, as you can imagine, 2 types of integers, that's 32 and 64 bits, 2 types of floats, 32 and 64 bits. And we had a specification that would provide instructions to manipulate these types and load instructions to manipulate the memory. The memory is what we call the linear memory. It's literally just an array of bytes. So, what can we do? Actually, we can already do a lot of stuff. We can certainly already compile something like this, right? We have an array, vals of doubles, and we have 2 functions, one that stores and one that fetches the double. And if you ran Clang nowadays, you will be able to get something out of it. So actually, you can already try these kind of things in Compiler Explorer. And I'm just going to go through so you have an idea of what it looks like. So just very quickly, local get will get a local from the stack. All the arguments to a function are put on the stack automatically. And local get will get the first argument from the stack. We synthesize in line 3 the constant 3 and put it on the stack. Then we call SHL to do a shift left on the top two values in the stack, and we put the result back in the stack, etc., etc. We go on, and then one of the things that you might wonder is what is that F64 store 0? So the store is basically obviously stores something into memory, and 0 is actually the index of the memory, because there was this idea that you could have inside the WebAssembly module many linear memories provided by the host system, and the 0 is the memory you're going to use to store the top 2 values on the stack. So one is going to be the index in the linear memory that you want to store the value, and the other one is going to be the value itself. So fetch double is more or less similar, but instead of having a store, we have a load instruction. Okay, so this is what already exists. But WebAssembly is an evolving language. The specification of WebAssembly keeps evolving, had new features. Proposals and discussions on proposals, etc., are all online. The discussions about which proposals should be accepted into the main specification is done online. And for the last couple of years, we've had many accepted proposals, and many of them are still being discussed and accepted. So one of those that we're interested on is reference types. So this means what if the double that we had there, that array of doubles, is a JavaScript value, is a value that is sent from the host system and that we have to deal with. So reference types are interesting. So first, they are opaque and host managed, and even though they can be arguments of functions and return values of functions, they can be stored to globals, but they cannot be stored to linear memory. So because they don't have a bit representation in memory, so you cannot just store to linear memory like, let's say, an integer or a float, etc. There are two different types. One is the externref, which is completely opaque, you cannot do anything with it, and the other is funcref, which is an opaque reference to a function that exists in the host system, and the only thing you can do from the WebAssembly side is call it. So that code there will not work. Why won't it work? Because we cannot store JS vals to linear memory, so that JS val vals is not valid. So how do we store reference types in WebAssembly? Well, that is, okay, so one of the things that we're trying to do here, or actually the main challenge here, is how to represent all of these types throughout the whole tool chain, not just in LLVM, but also in Clang. So how do we store these values? The reference types proposal introduced something called tables, which are sort of like something even a bit stranger than the reference types themselves, because they're sort of like arrays to store reference types, but with a bunch more constraints. Like, for example, you cannot store tables anywhere. You cannot pass tables into functions, out of functions. They're basically just a global static storage thing for reference types. So it's almost like the memory for reference types, but it cannot be the linear memory itself because, again, reference types don't have a bit representation. Okay, so let's see this example. So this is the same as the previous example, but now I replaced JSVal to our explicit type. Let's call it externref. So this is part of our proposal to extend C and C++ with WebAssembly reference types. So we have an array of externrefs, and we give it the attribute wasm table. And we do, again, a store and a fetch, and we would expect something like that to be generated. So we basically just get the first two arguments of the function to store, and we call table set. That's it. So now, how is this done in LLVM IR? So this has landed. This was part of our work last year, has landed, and the way we represent these things in LLVM IR is through the use of address spaces. So we have non-integral address spaces so that you cannot do things like pointer to int and integer to pointer. And all values of externref type are just pointers to address space 10. All values of funcref type are just pointers to address space 20. And then we define tables as module level arrays in address space 1, simply because we need an address space that will tell us, that allows us to identify an object so we can implement some semantic constraints like you cannot do certain things with it. Okay, and this is relatively straightforward because then we can lower these to the respective MVTs and then generate WebAssembly code. Okay, and then to manipulate these reference types, we have in LLVM a bunch of intrinsics like LLVM, wasm table, set, externref. We have similar ones for funcref. And if you use nowadays, sorry, it's not moving. Yeah. So if you use nowadays Compiler Explorer and you write down this LLVM IR, you get already the code that we expected to get earlier on. So this is fine. So, but what's the story in Clang? So what do we want to do? We want to be able to tell the user, the C++ developer, that they can write C++ code and can access objects from the host system and manipulate them. So we need a way to represent reference types in C and C++, and then a way to lower them to LLVM. And this is sort of like has been the theme of our work throughout this year. So there are initial prototypes, and it's not complete. And actually, I am aware that there is work, so other people have faced similar problems. I know that there is some resemblance of the constraints that we have with reference types, for example, with ARM scalable vector extension. And there is also some discussions about SPIRV types representation that sort of overlaps a little bit with the problems that we're having. And so we're also following the RFC about these, about opaque types, which, if I'm not mistaken, just a couple of days was renamed to target extension types. So we're not the only ones who have similar problems, and the idea is that we're going to try to work together towards a solution. But the way we're representing this in our tests nowadays is to have a new type for externref. We implement all the semantic constraints in SAMA, and then we lower this, as said, to an LLVM as a pointer to address space 10. And similarly to funcref, except it's not a new type, but it's just an attribute to a function pointer. So that then we can just call that function and lower it to address space 20. Okay. The problem, tables are sort of like what has been taken most time for us. Because tables almost feel like arrays. But then when we try to implement them as arrays, so using array surface syntax and array lowering, and so that's the first bullet point, representing tables as arrays and then using array subscripts to do store and loads from tables doesn't work so well, because at certain optimization levels, Clang is going to mess up array subscripts because the semantics of C++, C++ arrays is not the same as C++ tables, and changing all the places where the semantics are not the same is quite a huge amount of work, and you always run the risk of not catching all of them. And so, alternatively, we tried to do instead, okay, it's very interesting, you know, it's very nice for the user to have tables as arrays, but what about instead of lowering these to array subscripts, so accesses to the table, let's lower this into a new node that's a table subscript. And this is done also like that for matrix types. That was added a couple of years ago. There's also a matrix subscript. The problem with this is that there's actually quite a bit of work to be done when you implement a new AST node, like implementing new debug information, ABI information, etc. And we're actually quite keen on having an end-to-end example, and therefore we want a solution that's slightly quicker to get there. And the solution, which is not as ergonomic, but it's a quicker path to our goal of having something, is actually forget about array store and load using an array syntax. Let's just use intrinsics. And so actually we have solutions for these three cases. So we have a patch upstream for our first case, which doesn't work so well, so we'll have to review it. We have a work in progress patch for the second, where we implement actually a new node for Clang called table subscript, and we're trying out the third approach. And our hope is that we will actually get something quickly using the third approach, so an end-to-end example of using reference types all the way from C++ to WebAssembly. And if we can get this end-to-end example, then we can work out, where we want to go from here and work on a more or a nicer solution using the second approach. Okay, so our problems don't end here because there is a new proposal called WebAssembly garbage collection. So the WebAssembly garbage collection is a proposal that's introducing the definition of new types. That's array and structs. What this means is that now we can create types in WebAssembly or that are garbage collected in the host system. So this is, by the way, unrelated to GC support in LLVM. And this new proposal has instructions to manipulate these types. And a lot of the work that we're doing at the moment is how can we represent these types, which are potentially an enormous amount of types, depending on the application that we're compiling, in LLVM. But obviously, we want, in the next year or so, to bring all of these to Clang as well. So the current problem is that we cannot use the same approach we used before of saying, you know what, there's a new type, there's a new address space. Because, potentially, and if you think about LTO and everything else, you might have, all of these, everything in a single WebAssembly module. You might have potentially thousands, not millions of new types. So the problem is that we need to produce correctly typed, locals, function references, arrays and structures, function arguments and return values. And we need to keep these types throughout the LLVM backend. And obviously, having a new MVT for each type doesn't work. So the key property is that we don't lose track of the type of a value. If we define a new struct, and that struct has a couple of fields, and then we have a value of that struct that we're passing around, we need to keep track of that type throughout the backend. And the way we're doing that is we're assigning. We have a metadata table at the module level, and for each canonical type, we're assigning a new address space. So I just said that we're not going to assign address spaces, but because this is a prototype, that's what we're going to do now. So for now, to experiment with this solution, we intend to use address spaces for canonical types, but not necessarily, obviously, one for different values. So if we have two values that have the same type, we'll only use one address space. And we sort of like make everything into one. Okay, so this is the kind of example that we intend to work on, to have working on. We have some downstream patches to already implement these, where instead of having the address space 10 and 20 for externref and funcref, when we have an externref value, we'll assign it one address space over 255, and then we'll have a module level metadata table that will tell us what address space. So there's another example, I'll just skip it through because we're reaching the end of time. And the last thing that I wanted to mention is that there's also string refs, which is another proposal that we want to support, which are basically garbage collected strings from the host system. But these will introduce no issues because we can reuse the same type of solution that we had before. And so this is the summary. The reference types in LLVM is implemented, it has landed. So we have patches for the second reference types in Clang, and then We're sort of like working through the remaining items, and the last two is still a lot of research and prototyping, etc. So yeah, thank you very much. We're hiring in case this kind of work interests you. Thank you very much.